traveling more than 2,600 miles per hour.
We've mapped it. We've photographed every inch of it from orbit. We've sent rovers across its surface. We've walked on it, driven on it, collected rocks from it, and brought them home to study under microscopes. And yet, the moon is still hiding something. Not something buried deep underground. Not something locked behind atmospheres or oceans. Something sitting right there on its surface, in plain sight of every telescope and satellite we've ever aimed at it. The problem isn't that we can't see it. The problem is that we can't fully explain what we're seeing. And the deeper you go into the science, the more you realize how much of the moon's story is still missing. The moon has two faces. The side that forever faces Earth, the near side, is the one we've stared at for thousands of years. The one that inspired myths and calendars and poetry. Familiar, mapped down to the meter. Then there's the other side, the far side, the side that never faces Earth. The side that remained completely invisible to human eyes until 1959, when a Soviet spacecraft called Luna 3 swung around and captured the first photographs. What those photographs showed was wrong. Not wrong in a terrifying way. Not wrong in a conspiratorial way. Wrong in the way that makes scientists sit back in their chairs and say, "Wait, this doesn't make sense." The near side of the moon is covered in dark, smooth plains. Ancient seas of frozen lava that formed billions of years ago. We call them Maria, from the Latin word for seas. They cover about 30% of the surface we see every night. The far side has almost none of them. The far side is brutalized, cratered beyond anything on the near side, ancient, rough, pale, a completely different world. And it's the same moon, same age, same formation event, same distance from the same impacts. Different surface. For over 60 years, that asymmetry has been one of the deepest unsolved problems in planetary science. Then, in 2025, something changed. Artemis II, NASA's first crewed mission to fly around the moon in more than 50 years, carried 4 astronauts on a trajectory that swept them around the lunar far side in a path no human crew had ever flown before. For the first time in history, human eyes were looking down at the far side from close orbit. And what they documented, the photographs, the spectral observations, the geological surveys from above, added new pieces to a puzzle that science has been struggling to complete since the Cold War. Not final answers, new clues, better clues. The kind of clues that narrow down the possibilities and sharpen the mystery at the same time. If this is the kind of exploration that keeps you up at night, you're in the right place. Subscribe, and we go deeper every single week. Let's talk about what those clues actually look like. Because the far side of the moon isn't just more craters. It's a crime scene, and every feature on that surface is a piece of evidence. Start with the craters themselves. The far side hosts the largest confirmed impact crater in the entire solar system, the South Pole Aitken Basin, roughly 2,500 kilometers across and more than 8 kilometers deep. So large that material from the moon's lower crust, possibly even its mantle, was excavated and scattered across the surface. That impact happened between 4 and 4.3 billion years ago. The rock it exposed hasn't been significantly touched since. What the Artemis II observations help document is the spectral signature of that basin's floor, the color and reflectivity of the exposed material, giving scientists sharper data on its mineral composition. The far side's ancient crust, laid bare by the biggest impact any world in our solar system has ever survived. Then there are the lava plains, or rather, their absence. On the near side, ancient volcanic eruptions flooded the low-lying basins billions of years ago. Molten rock poured up from deep inside the moon, cooled, and formed those dark, flat maria we see from Earth. The far side should have had the same eruptions, the same internal heat, the same volcanic history. But the lava never reached the surface in the same way. Why? One leading hypothesis involves the moon's crust itself. The crust on the far side is significantly thicker. In some regions, nearly twice as thick as the near side. When magma pushed upward from the lunar interior, it may simply have run out of force before it could punch through. The lava that shaped the near side over and over again stalled beneath the far side and never made it out. The moon's own thickness stopped its surface from being resurfaced. That's why the far side looks so ancient. It's wearing its original skin. But here's where the science turns into something that feels more like detective work. You can't just land everywhere and drill. You can't just pick up every rock you want to analyze. Most of what we know, most of what we're learning, comes from reading light. When sunlight hits the lunar surface, different minerals absorb and reflect different wavelengths. Olivine, pyroxene, feldspar. Each one has what scientists call a spectral fingerprint, a precise pattern of light absorption that identifies it as clearly as a DNA sample. The Artemis II crew carried and deployed instruments designed to read those fingerprints from orbit. What they were mapping was the chemistry of a world that hasn't been significantly disturbed in 4 billion years. Subtle shifts in color, barely perceptible to the naked eye, mark the boundary between ancient highland crust and the scattered ejecta from major impacts. Variations in brightness reveal where the surface has been churned by micrometeorites over millennia versus where it has remained pristine and compacted. Texture variations seen in high-resolution imaging hint at buried structures underneath. Ancient impact melt sheets, collapsed lava tubes, ridges that formed as the moon's interior slowly contracted and cooled. Each of these features is a sentence in a story written in the language of geology. And the scientists trying to read that story are doing exactly what detectives do, looking for anomalies, looking for places where the evidence doesn't fit, looking for the clues that the surface didn't mean to leave behind. The ridges are some of the most striking. Across the far side, there are long, sinuous formations called lobate scarps, wrinkled cliffs that rise tens to hundreds of meters above the surrounding terrain, stretching for hundreds of kilometers in long arcs across the landscape. These aren't impact features. They're tectonic. They formed when the moon's interior cooled and contracted, causing the crust to compress and buckle slightly. Like the skin of a drying fruit, the moon shrank. And those scars on the surface are the record of that shrinking. But here's what makes them important to the larger mystery. The lobate scarps on the far side appear in different distributions and orientations than those on the near side. Some of them cut across ancient craters, which means they formed after those craters did, recording tectonic activity that happened hundreds of millions of years after the initial bombardment. The moon was still geologically active far longer than our early models suggested, and the far side, untouched and unresurfaced, preserved that evidence in ways the near side, repeatedly flooded and reshaped by lava, simply could not. The far side is a geological time capsule, and we are only now beginning to learn how to read it. There's one more layer to this. The asymmetry between the moon's two faces may have shaped our entire existence here on Earth. The near side's volcanic history, those mare basins, those vast lava plains, created the gravitational and surface conditions that locked the moon into its current orientation. The heavier near side faces Earth because physics pulled it that way. Because the internal distribution of mass, shaped by volcanic activity that the far side never experienced, created an imbalance that tidal locking over billions of years turned into a permanent feature of our sky, which means the moon you see, the face that reflects sunlight into your bedroom window at night, the face that pulls the tides, the face that sailors navigated by for 10,000 years. is the direct result of a volcanic asymmetry that science is still trying to fully explain. The far side's hidden nature isn't just a geological curiosity. It's the negative space that defined everything we see. Tell me in the comments, does it change how you look at the moon tonight, knowing that the side we've always seen was shaped by forces we're still unraveling? I'll read every single one. The problem isn't that the dark side of the moon is mysterious. The problem is that the more clearly we see it, the more precisely we read its craters, its chemistry, its ancient scars, the more we understand how much of its history is still locked away in rock we've never touched, in minerals we've mapped from orbit but never held in our hands. The Artemis missions are giving us new sentences in that story. But the story is 4 billion years long, and we have only just learned how to read. Keep looking up.